Hi friends, so in this video I'm going to talk a little bit more about the sign of curvature. So in the video number 3 I talked about the curvature formula and we actually derived it and we reached this point, after which I said this is given by c theta cross c theta theta upon the magnitude of c theta the whole cube. And this is actually wrong because as you can see it should be c theta theta cross c theta upon the magnitude of c theta the whole cube. And in fact this is also wrong because this would suggest that it is a vector quantity, while if you see the original formula here, it is a scalar quantity. There is no I, j or k in it. So what the right thing is, we have to take a determinant of this. And this is our actual curvature that we derived. And let's look at what the sign of this determinant would look like for different curves. So let's say we have a circle here, something like this, and then uh, we let's say we take a unit normal somewhere here, okay, and then along this unit normal what we'll see, the curvature is actually given by this thing here, okay. So the this would be something like k into the unit normal, and as you can see this is in the opposite direction, so we are taking our curvature along the outside normal, but here in this case we see that the direction would be along the inward normal because that's how we formulated it. So conventionally speaking, for a shape like this, a circle or an ellipse, we want the curvature to be always positive. That's the convention. So what we are going to do is instead of applying along the outward normal, we are going to apply the curvature along the inward normal. And in order to do that, we'll have to apply a negative sign to our derived quantity. Okay. And upon the denominator, whatever that is. So this then is given by something like the determinant of c theta cross c theta theta upon the magnitude of c theta to the cube. So this is the more conventional way to uh, talk about the curvature. And as you can see, for a shape like this ellipse or a circle, this quantity is positive, and we apply it along the inward normal. So in many curves it won't be sensible to talk about inside and outside. So because of that we have some conventions for the parameterization. So for this we say something like along the increasing values of theta, which is our parameterization, uh, the curve, the inside of the curve is towards its left, so this would be left, and the outside everywhere is considered right. Okay, so this is right. Doesn't mean actually literally right. Even the left side of the curve is right. Okay. So the way to think about this new conventional formula is whenever the normal is going, the curvature is going in the left direction, that time we consider it to be a positive curvature, and whenever it's going in the outward direction, that time we consider it to be a negative curvature. And it's given by these two formulas here. Traditionally this is the one that we'll be using a lot, so c theta and cross product with c theta theta. So that's the one, and I'll cover an example to like solidify this understanding. So consider a curve that is parameterized by theta in this way. So the x is given by 1 by theta and the y is given by cos 2 pi of theta. So what we'll have for different values of c theta is at 0 we'll have 1 and this will be 1, right? And then at half we'll have, sorry, not minus half, just half. We'll have half and minus 1, and for 1 we'll have 0 and 1, and then the curve will basically repeat itself. So the theta goes from 0 to 1, and then it repeats itself. So it's not a closed curve, but it has the same properties because it's a periodic curve. So we can have, now this is my version of a cos function. It's pretty bad, but consider it to be a cos like this, and it's in, this is our x, this is our y, and the value of theta changes in this direction, which means this is our left and this is our right. And as we know, the outward normal is always going to be going in the right direction. That's the convention. However, the curvature, you can see if I draw a circle here, it would be like this. So the curvature is here, here the circle would be here, so the curvature would be here, and here again the curvature would be here. And now what we have understood is that whenever it's the curvature's direction is in the left, that time it is positive. So it's positive here, positive here. However, in this case, it is negative. So whenever it is along the outward normal, it is negative. Whenever it is in the opposite direction, whenever it is along the inward normal, that time it is positive. And it is nothing but a scalar quantity, because as we know, CSS is given by Kn, and n is the actual normal here, and k is the quantity of curvature. So we look at its magnitude along with the sign to determine where how the curvature is, and the sign is also really important, as we'll see in the future videos where we start talking about how shocks can be formed if we evolve the curve without considering the curvature, and how if we consider the curvature in our speed function, then we have a smooth wavefront which we can build. So this is all I have for this video, and we'll talk more about this in the future videos. Thank you.